All right, so I think let's get started. So the final reminder for homework number 8, that's due tonight, okay? And then I believe number 9 is up online now. It's due next Tuesday, okay? So if you finish number 8, you can start working on number 9 if you have time. All right, and then for the current plan is still to have exam 3 next Friday next week, okay? If we go back in person for the lecture, then we also have exam number 3, okay? Um, so let's take a look. Last time we learned torque, which is basically defined as the R times F, okay? If R and F are perpendicular to each other, then that gives you the magnitude, okay? And we use symbol tau as torque, right? So then torque equals to I times alpha. For the torque, the direction wise, it's defined by right-hand rule. For the it's equal to the cross product of the R vector times the cross the force. Okay, then you use the right-hand rule to determine the direction of it. Now, in general, R and F are not perpendicular to each other, so they may have an angle that is not 90 degrees. So then the magnitude for torque will be R times F times sine of theta. Okay, theta will be the angle between R and F. Okay, as indicated in this figure over here. So then for the Newton's second law, this is similar to the second law in linear motion. In linear motion, F equal to m times a, mass times acceleration. In this case, the torque equals to moment of inertia times alpha, okay? And for multiple torques, you sum them up and equal to I times alpha, okay? Again, keep in mind the tau should be a vector quantity, so also direction that should be the same as the acceleration, okay, angular acceleration. All right, and then we talk about work and power for rotational motion. So similar to what we have in linear motion, then work done in a rotational motion is equal to torque times the displacement, angular displacement, okay? And then the power will be time derivative of the work, okay? Or equals to tau times omega after the derivation if tau is constant, okay? So then that's the case there. All right. And we talk about work energy theorem. So basically similar to what we learned in linear motion. So rotational kinetic energy change should be equal to the work done by the torque. Okay, so it's the same there concept. You can also calculate the work done by a particular torque. If it's varying with angle theta, then you can do integration over here. Okay, so that's on that. And then we talk about if an object that is having both linear and rotational motion, so then it will have both linear and rotational kinetic energy. So then the total kinetic energy will be summation of both, okay? So 1/2 mv squared plus 1/2 I omega squared. If this is a rolling motion, in which we'll talk about it later, then V and omega has a relationship of omega equal to V over R, or V equal to R times omega. Then you can rewrite the total kinetic energy should be a multiple of linear kinetic energy. Okay, so linear kinetic energy multiplied by 1 plus moment of inertia of the object divided by mr squared. Okay, all right. So we'll start with another exercise over here. So this one is about work and energy theorem, but in rotational motion. Okay, so for part A, so this one says in part A, it says a cord is wrapped around the ring of a solid cylinder of radius 0.25 meters. So for a solid cylinder, if it's rotating around the x rotation through the center, then it's similar to a disk. Okay, so then moment of inertia should be 1/2. Let me see. It should be 1/2 mr squared. Okay. So, and then also it tells you that so if a constant force is applied over here, so a constant force then will result in a torque on this disk. Okay. Then if the core is displaced by 5 meters. Okay, so then you can calculate what would be the corresponding angular displacement theta. Okay, by doing like arc so this is 5 meters, but pretty much the arc length. Okay, the s divided by r should give you the angle. All right. Oh, it actually tells us the moment of inertia. Okay, so that's moment of inertia is given 6.0 kilogram times meter squared. So you don't have to calculate moment of inertia, it's given. Okay, so it's asking you use the work energy theorem to calculate the angular velocity of the cylinder after 5.0 meter of cord has been removed. Okay, and then in part B, say if this is then replaced by a 40 Newton weight, what's the angular velocity? So in this case, then you'll be doing like what we did last time. You will apply conservation of energy. Okay, so linear energy and then rotational energy. So one of the example we went through last time is about that. So if you remember, a bucket was hanging under a rope, and then that rope goes through the a pulley. Okay, so you can refer to that one to see how you can solve for this one. Okay, I think I'm going to have you guys try out this one, giving you guys several minutes, and then if you have your answer, you can click on the problem to submit your answers there. Okay, we can take a look at the solution together in a few minutes. Oh, actually, on part B, I think it's easier to just use conservation of energy. Okay. Um, You can also refer to like what we done last time on the bucket hanging under a pulley with a string, but that might be more difficult to do in that way instead of doing conservation of energy. Okay, it would be easier to use conservation of energy. I'm gonna to wait for another 1 minute or so before we check on the solution together. Okay. All right, so let's take a look here. So if you have a force here, then the resultant will be there's a torque over here. Okay, so there will be a torque, and then it goes like 5 meters. So then there's a certain angle involved. Okay, so we can apply work energy theorem here, which says the final kinetic energy minus the initial kinetic energy should be equal to the torque times the angular displacement. Okay. So the initial, this is 0, so the initial that goes to 0. Okay. Now the theta that could be related to the 5 meters, the s divided by r. Okay. So then it will be the 5 meters divided by the 0.25 meters. That would be 20. That's in radians. Okay. So if it's dimensionless, that means it's in radians. All right. So then it gives you I, you're looking for omega, right? So you can solve for that. And then the torque should be equal to R times F. In this case, R and F are perpendicular to each other all the time. So this is 0.25 meters times 40 newtons. That would be 10 newtons times meters. Okay. So then 1/2 I omega squared equals to tau times theta. So then omega equals to multiply by 2 on both sides and then divide by I. Okay, so that gives you omega squared equals to 2 tau theta over I. Okay, then you'll take square root of it. So to give you the omega. Okay, so 2 times the 10 newtons times meters times the 20 radians divided by I is given as 6. Okay, so then everything is in SI units, so your answer should also be in SI units. So 8.16 radians per second, that will be your final angular speed, okay, angular velocity here. So that's part A here. Okay. Now on part B here, now things are a little bit differently. Okay, so you have again that disk, and then there's this weight, kind of, yeah, not exactly as the figure shows, but this guy is 40 newtons. Okay, so after this drop 5 meters, then there's kinetic energy gained by this and then also by that. Okay, so now you can see in this case, so then if you look at the free body diagram, mg here and then t there and then there's a t there. Okay, this t should cancel out each other. Okay, so that doesn't really matter. So that tells you the work is only done by the mg. Okay, so you can apply conservation of energy, but in this case, mg is equal to 40 newtons. So then you can calculate what's the m first. The mass of the weight will be 40 newtons divided by 9.8 meters per second squared. That will give you your mass in kilogram. Okay, so 4.08 kilogram. All right, now we are going to just so this is the initial, okay, and then final, this guy dropped like 5 meters. Okay, so that's the final, that's the initial over here. Okay, so because we are going to apply conservation of mechanical energy, Ki plus Ui equals to Kf plus Uf. Okay, the final is at lower level, so we can take it as ground level. So that means U final is 0. Okay, Ui on this guy then will be the mg times the 5 meters. Okay, mgh or mgy. Okay, and then for the potential energy for this disk here, because its vertical position doesn't change, so you can leave them that out because it will cancel out initial and final. Okay, when you set up the equation on two sides. The kinetic energy, however, so initial kinetic energy should be 0 because they are let go from rest. So initial is 0. Okay, so then for this guy, Ki is 0, so 0 plus mg times 5, okay, or 40 times 5 because 40 is equal to mg, so 40 newtons times 5.0 meters. Okay, that should equal that plus the, oh yeah, this is no, that's the already the mg, the ui. Okay, that equals to K final when this weight is dropped by 5 meters, there's a linear kinetic energy on this guy, so 1/2 m v square plus also this disk now will have rotational kinetic energy 1/2 I omega square. Okay, and then plus u final will be 0. Okay, now because these two are connected, so then omega of this guy and then the v should have a relationship of so v equals to r times omega. Okay, so now you can write as this. So this is 200 on this side, 200 joules should be joules. Okay, so this is 1/2 times m times r omega square plus 1/2 times I times omega square. Okay, so this is 1/2. The mass is 4.08, and then r is 0.25 meters. Okay, I'm going to leave out the units because I know everything is in SI unit already. Okay, so square omega square plus 1/2 times 6 omega square equals to 200. Okay, so this one and this one will combine. Okay, and then the omega final will be solved then. Okay, so it'll be 200 on this side divided by this one combined plus that one. So 1/2 4.08 0.25 square plus 1/2 times 6, which will be 3, okay, equals to omega square. Then you are going to take square root of that and then square root of that. Okay, so your answer should be about 8.0 radians per second, okay, equals to omega. All right, so that's on the second part. Okay. I'm going to pause for a few seconds to see if you guys have questions. Okay. All right. So if you guys are clear, we can move on. So I'm going to just talk about the first section of chapter 11 for today, and then the remainder of the chapter we'll talk about it on Friday. Okay, so I think the first section in chapter 11 is more related to what we learned in chapter 10. Okay, so I'm going to put this section together with chapter 10. Okay, so as I mentioned earlier, sometimes when the object is moving, it might have linear motion and then rotational motion at the same time. Okay, so for example, for a bicycle wheel, if it rolls across the floor here, then it's rotating with its axis going through its center. But at the same time, the whole wheel is moving linearly towards the right. Okay, so that's that tells you this wheel has both rotational motion and then linear motion. Now, in the scenario that the wheel is not slipping, so that means it's not slipping when it's in contact with the floor. So then um, v is equal to linear speed, v will be equal to r times omega. Okay, so that's the case there. I would like to point out that at the contact point over here, okay, so if you just look at the linear velocity alone, at this point, this point on the wheel here actually has 0 linear velocity. It's not moving with respect to the floor, okay? That's when it's not slipping. If it has relative velocity with the floor, then it's slipping, okay? So you can consider the whole wheel as the combination of velocity, linear velocity on the center itself, and then combining with the rotational motion, okay? So you can imagine everything is moving with velocity v towards the right, but at the same time, the wheel is moving in that direction. So then at that point, you can see there's a v in that direction, and then there's, if you look at the rotational motion, this guy is going to the left, okay? So the velocity will be r times omega, but in the opposite direction. So these two velocity cancel out. That's why at this point, the velocity is 0, okay? At the center over here, the velocity, linear velocity is v. At the top of the wheel over here, it's going to be twice of v actually, okay? Because it's the overall v plus r times omega, okay? So going to be twice of that. So that's what happens when you have a wheel that's rolling, okay? All right. Now, rotational speed you can calculate if you know how much time the period of the one full revolution, and then so that can be 2 pi r divided by t. Okay, and then also for linear speed of the whole, it's going to be equal to the r times omega angular speed. Okay. Okay, so exactly this is what I just discussed earlier. So you can treat as like the linear motion plus the rotational motion. Okay, so rotational motion, at different points of the wheel, the velocity is in different directions. Okay, so in this guy, it's all going to the right. This guy is going to the left. Okay, but for the linear motion, so this is a linear motion. Everything is going with velocity v towards the right. Okay, so then for the top of the wheel, it's twice of the what you have at the center, but at the bottom of the wheel is 0. Okay, so that gives you that. An idea of why the velocity is 0 at the contact point. Okay, and then you probably remember that when I mentioned the friction, if you have wheel or tire that is not slipping, then the friction force, we are considering it as static friction because the velocity is 0. So that means no relative velocity at the contact point. Okay. All right. So when you have rolling motion, if there's no slipping and if an object rolls down the inclined surface over here, okay? So you can see because there's no friction here or no kinetic friction here, I should say, because there's always static friction to keep it rolling down, okay? So if no kinetic friction, then work done by friction is 0. So then if an object rolls down the inclined surface like this, the kinetic energy should conserve, or the mechanical energy should conserve. Okay, so let me derive this guy on the paper here. So an inclined surface over here. All right, it rolls down there, radius r, and goes down there. At the bottom here, it will have a v linear speed, and then as well as a rotational speed omega. Okay, so omega then should be equal to V over R, or the other way around, V equal to R times omega, okay? So either way. So you can apply conservation of mechanical energy here. Take this U final as 0 because that's the low point, and then U initial then should be mgh, okay? Now if it starts from rest, K initial is going to be 0, K final now is going to be 1/2 mv squared, right, for the linear motion, but plus the 1/2 I omega squared for the rotational motion, okay? So you're going to set up that ui plus ki is equal to uf plus kf. So that mgh, which will be ui plus 0, is going to be equal to uf will be 0 plus 1/2 mv squared plus 1/2 I omega squared, okay? Now, as we mentioned earlier, you can rewrite this, okay? So that becomes 1 plus, so in this case, this is equal to omega is equal to V over R. So V over R squared. Now let me just slow down. Plus 1/2 I times V squared over R squared. Okay. And then you can rewrite this term as so 1/2 mv squared plus 1/2 mv squared, right? If you put an m here, you want to divide by m, right? Now you still have I remaining somewhere. So on the top there, and then R squared should be still here, okay? So then this becomes, okay, so there's this term multiplied by this guy, okay? So it's 1/2 mv squared multiplied by this guy, okay? So then that's 1/2 mv squared plus 1/2 mv squared times I over mr squared. So then the left hand side you have mgh, the right hand side you can have 1/2 mv squared of 1 plus I over mr squared. Okay. Now you can see this m and this m will cancel out. Okay. So the 1/2, you can put the 2 there, okay, to cancel out the 1/2. All right. Basically, try both sides multiply by 2, leaves a 2 here, but 1/2 will cancel out the 2. Okay. And then you can solve for the v square. So then v square is equal to, you divide both sides by this guy. So 2gh over 1 plus I mr square. Okay, I will be the moment of inertia. Okay, so then v will be equal to square root of that guy. Okay, so that tells you v is equal to square root of 2gh, right, divided by I, or 1 plus, divided by 1 plus I over mr square. Okay, so this is basically what is showing on the PowerPoint slide. Okay. So in that sense, if you have two objects, okay, the same mass, the same radius, but different shapes, one is a ring, one is a disc, okay, so then you can predict like which one actually reaches the bottom first if they both rolls down the inclined surface without slipping. Okay, so basically you are going to see which one would have larger velocity at the end, right? If it has larger velocity at the end, then the overall averages velocity of the object would be larger, right? So then it takes less time. So larger speed, less time, right? To go through the same distance, right? Now, so basically, if you want to have larger of this v, so 2gh, that's constant, that remains the same, right? M is the same, R is the same. So the only deciding factor will be the I, okay? So if you have larger I, okay, if I is large, in this expression, you can see I is in the denominator and the numerator in the denominator. So if I is large, then V will be small. Okay, V is small. You are looking for a larger V, so then you need I to be small. Okay, so I is small, V is large. Okay, now compare for a ring and a disk, which one has smaller moment of inertia? So for the ring, I of the ring is equal to mr squared. I of a disk is 1/2 mr squared. So you can see the disk has smaller, right? I. So then the velocity at the bottom of the slope is larger. So that means the disk will reach the bottom first. Okay. All right. So we are going to take a look on this example here. So it says that a solid sphere rolls down this ramp over here. Okay, solid sphere has diameter of 0.17 meters, and it's released from rest and ramp rolls down here without slipping. Dropping through a distant vertical height of 0.61 meters, the ball leaves the bottom of the ramp, which is 1.22 meters above the floor, moving vertically. So when it leaves here, it's vertically. Through what horizontal distance d will the ball does the ball move before landing? So we are looking for this horizontal distance d. And then how many revolutions does the ball make during its fall? So as it falls down, how many revolutions? So it's just from here, from the table to the floor here, okay? So you can see this is, there are two parts of the motion here. The first one is the rolling motion, it rolls down. And then the second part is pretty much a projectile motion, right? Which the ball is actually spinning, okay? All right, so I think, so you're going to divide this into two parts. The first part is when the ball rolls down the ramp, okay? So you can apply conservation of energy, but this time also include rotational kinetic energy there. And then the second part is simply projectile motion, okay? So I'll give you guys a few minutes and then we can take a look on the solution together. So for moment of inertia for the solid sphere or ball, it should be 2/5 the mass times radius square. Okay. All right. I think let's take a look on the solution together here. Okay. So, as I mentioned, there are two parts of the motion from A to B. You want to do the conservation of the energy. Okay, because it rolls down without slipping. So that means there's the only, because normal force again will do zero work. Okay, and then there's just static friction. So static friction also does zero work because and there's no relative motion. So di is equal to zero. Okay. Now the only work done by it will be the gravitational force, which is conservative force. Okay. So then you are going to do UA plus KA equals to UB plus KB. Okay. We'll take this as the low point where UB is going to be 0. So then UA is equal to mg of h, this h over here. Ka should be 0 because it released from rest. Okay, and then Kb then will be equal to now two parts. That's 1/2 mv square less 1/2 I omega square. Okay, and then keep in mind that V should be equal to R times omega from A to B. So from A to B, okay, you have that UA plus KA equals to UB plus KB, where UA is MGH, and then KA is 0, UB is 0 plus these two combined. Okay, so if you remember that those two combined should be MV square 1 plus I divided by MR square. Okay, combination of the kinetic energy and rotational energy. And then I is equal to this guy. So I is going to be this guy here, goes in here. So then mgh is equal to 1/2 mv square of 1 plus, okay, 2/5 mr square over mr square. Okay, so it's basically just 1 plus 2/5. Okay, so this will cancel out that. And then also the mass will cancel out. So then GH is equal to 1/2 V squared times 1 plus 2/5. So this would be 7/5, right? Times 1/2 V squared. So that's 7/10 of V squared. That goes to GH, okay? So GH would be equal to 7/10 of V squared. Then V is equal to V at point B, so that's V there. That's equal to, so if you move this over here, it will be 10/7, okay? Square root of 10/7 GH, okay? You can solve for this V. So 10/7, 9.8 meters per second squared times 0.61 meters. So V at the bottom here will be equal to 2.92 roughly meters per second. All right. Now then, from B to C here, this will be a projectile motion. You can set up that the origin at point B, the X in this direction, the Y in this direction, okay? So then in Y direction, the Y is going to be equal to, so this is 0, Y equal to Y0 plus V0Y, right, times T plus 1/2 GT squared. X then will be equal to x0 plus v0x times t. Okay, so those two equations. Because you set a point B to be the origin, so this is 0, this is also 0. Okay, now this ball leaves the ramp over here with horizontal velocity. So initial velocity y should be 0. And then this is v, just v. Okay, so you're looking for this d, which would be the x here. So then that's your x will be your d. Okay, you know the v, now you need to know t. Okay, to solve for t, you'll turn to this equation to solve for t, because y is given as 1.22, that's the height here, and then g is constant, so you should be able to solve for t from there. Okay, so 1.22 meters equals to 1/2 9.8 meters per second squared times t squared. All right, then solve for t. I think you guys can do that. I'm going to just skip a couple of steps there, but that should be equal to square root of 2 times 1.22 meters divided by 9.8 meters per second square, okay? Which is going to be 0.499 seconds, okay? Then D is equal to V times T. V is 2.92 meters per second times 0.499 seconds. That would be roughly 1.46 meters. Excuse me. All right. So that's A here. B is asking you what would be the angular, or how many revolutions does it spins while it goes from here, point B to C. Okay, so there's angular velocity omega, right? So then you're looking for this guy. So for B here, you're looking for the angular displacement will be equal to omega times T. Okay, T is net T 0.499. Omega will be V over R. So then it will be V over R times T. 2.92 meters per second divided by the radius. It tells you the diameter, right? So just 1/2 of the diameter, 0.17 meter there, times the T, 0.499 seconds. Okay, that gives you how many in radians, the angle in radians. You're looking for how many revolutions. Okay, so then divide by 2 pi. That gives you, so that's 2 pi radians per revolution. Okay, so that will give you how many revolutions? Roughly 2.73 revolutions. Okay, on that part. So this is A, and this is B. Okay, that's kind of a picture of this solution. All right. Any questions you guys might have?
Excuse me.
Yes.
Just really quick, can you verify how you did the inertia of the sphere and got 2/5 mr squared?
Yeah, that's something you can look up from the table, the picture table we saw like a couple lectures ago. Okay, so that's something you look it up.
Okay, thank you.
Yep. All right, so if no more questions, we will stop here for today. Okay, and then I'll see you guys on Friday again online. Okay.